Hello, we start our course with a paragraph about vector spaces. Let us have some set X, and we also consider fields of real or complex numbers. So real numbers, complex numbers. We will call X vector space, our this field or this field, if for each two elements from X we can correspond another element from X, which is called sum of these elements. So by doing this we introduce the vector addition operation, and also for each element from X and each number we correspond another element of X called product of X into alpha. And by doing this we introduce the scalar multiplication. And these two operations obey 8 axioms, what I will list here. X plus y is equal to y plus x for all x and y from x. X plus y plus z is equal to x plus y plus z for each x, y, and z from x. Third axiom, there is a special element called zero elements in X, such what X plus this element is equal to X for each X from X. So there is some special elements called zero elements or neutral element regarding the addition, such that if we add this element to any other elements from X, nothing changes. So this sum is equal to X. And last axiom regarding addition. For each element there is a special element from X sometimes called opposite element, such what X plus this opposite element gives 0. And 4 axioms what involves both addition and multiplication. Alpha multiplied to sum of x and y is equal to alpha x plus alpha y for each alpha and each x and y from x. Alpha plus beta x is equal to alpha x plus beta x alpha, product of alpha and beta multiplied to x is equal to alpha multiplied to beta x. Once again, for each alpha and beta from R, And the last action, special role of number 1. If we multiply 1 to any element from X, we obtain the same element. By 1 here, I assume a real or complex one. So in case of complex numbers, it's 1 real part of a number and 0 imaginary part. So if we have set and we can involve these two operations, sum and product, and all these 8 actions are fulfilled, once again we have vector space, our set of numbers. Some more definitions, and then we'll consider some examples. Let us have vector space, and let us have some set of vectors, group of n vectors. I forgot to say what elements of vector space traditionally are called vectors. We will call these vectors linear dependent if we can find non-trivial set of n numbers by non-triviality I mean what not all together, or not all these numbers are equal to 0. Can be expressed like sum of absolute values of these elements are bigger than 0. Such what linear combinations of these vectors with these numbers gives a 0 element. So if we can find such non-trivial combination of numbers, these vectors are called linear dependent. And the opposite definition, I will just change this. We will call vectors, set of n vectors, linear independent if we cannot find such non-trivial combinations of constants, such what this combination gives us 0. So it means it's equivalent to the fact that if some linear combination gives us 0 element, it happens only if all coefficients are 0. Only in this case we have 0 combination of these elements, so in case our elements are linear independent. Okay. Next next definition. We say what dimension of x is equal to d, and write this if we can find d linear independent vectors and we cannot find d plus 1 linear independent vectors. So each group of d plus 1 vectors linear dependent. So in this case we say what dimension of this space is equal to d. D here is some natural number. In this case we also say what x is finite dimensional space. And the last definition, we say what dimension of x is equal to infinity, or x is infinitely dimensional space, and write this if for any natural number we can find n linear independent vectors. So if we like, we can find 10 linear independent vectors. If you want, we'll like 1000 and so on. So each number we can show n linear independent vectors. So this is it for the theory, and next we consider several very simple examples. First example of vector space is a set of real numbers. In this case we can introduce sum of two vectors and product of vector and two numbers using standard rules of addition and multiplication in a set of real numbers. So x plus y is just numerical sum, and the same for alpha x. In this case, the dimension of obtained vector space is equal to 1. Little bit more complicated example. Let's d some natural numbers starting from 2, 2, 3, so on. Some given natural number. And let's consider the space of d-dimensional vectors. So elements of this space are arranged groups of d numbers, d real numbers. So sometimes these numbers are called coordinates, and these coordinates are from set of real numbers. In this case, sum is introduced component-wise or coordinate-wise. And also the product is introduced also coordinate-wise. Once again, we obtain element from RD. We can prove that in this case all axioms of vector products are fulfilled, and the dimension is exactly equal to D. Please prove it. We will discuss it during our meeting. Next example. Let's consider sequences. So sequences are infinite sets of infinite numerated sets of real numbers. So each key belongs to R or any key. For X in this case is such a sequence. So once again we can set the sum of two elements, in this case two sequences, also component-wise. So it is the following sequence. So another designation for this sequence is like this: x1, x2, and so on, xn. Unlike vector, here we have infinite number of coordinates. So sum of two sequences is defined like this. It is a sequence obtained by component-wise sums of corresponding elements from X and Y. And similarly for product. So once again we obtain two new sequences, sum and product for each X and Y, and for each alpha for R. There is no special designation for abstract sequences, so let's reduce just X. And the last example, I forgot to say what in this case we have infinite dimensional space, and also please try to prove it. And last example, let's consider a set of continuous functions on some given sigma segment AB. The A and B are some real numbers, and A is smaller than B. So this is set of continuous functions on this segment. Let us have two functions f and g from this set. Then sum of this function is defined element-wise, so it's f from x plus g from x for each x from the segment. And the same for product. So function alpha f is defined in the argument x as alpha multiplied to f from x. Once again for each x of a, b. It can be proved that in this case also all 8 axioms are fulfilled, and we obtain now a vector space. Once again, it is infinitely dimensional. And once again, you need to prove it. That's all about vector spaces. Bye.